So in last section, we were looking at inverses and isomorphisms. In this section, we're going to be looking at products and quotients of vector spaces. And all of this is going to come together in the next section. The next section is probably the one that students have the most difficulty with. So we have to make sure we understand this section, the matrices section, the invertibility and isomorphisms, so we can get a good grasp of what's going on here, not only here, but in the section that's to come. So we'll start with products and quotients of vector spaces. First, what a product is. So suppose V1 to Vm are vector spaces over F. Then the product, and you may have seen this before. You might be familiar with this from other classes, right? That's the product V1 to Vm. And we just define it like this. So V1 to Vm is every Vj corresponds to their vector space, right? As it says here. And how do we define addition and scalar multiplication? Well, how you would think we do. So this is a vector of the product space, and this is a vector. Then we just add the corresponding components. With the scalar multiplication, you just multiply lambda times every vector. And that's really just how it's defined. So an example, elements of polynomials at most degree 2. The product of that space and R3 are lists of length 2. Why 2? Well, because one comes from here, one vector, and the other vector comes from here. Right? So a vector in this space, in the product space, would just look something like this. A polynomial that belongs to the first space, and then a vector that belongs to the second space, and you put those together and make that list. And in fact, as you probably imagine, V1 to Vm, if we take their product of those spaces, it is a vector space over F. And I mean, you already know how scalar multiplication and addition is defined. I won't go ahead and prove that because, again, that's exercises from chapter 1. But I will tell you that the identity, the additive identity, well, it's just 0, 0, 0, 0, so on and so forth. For example, the additive inverse is just negative V1 dot 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 negative Vn, or how many? Yes, Vm. So just like use that information. I'm sure you know how to prove that something's a vector space. Just it's a good exercise to go through the process. But I do have a question. Is R2, the product of R2 and R3 equal to R5? And is that product space isomorphic to R5? Well, um, the an example. Sorry, I was kind of processing there. We will answer that fairly soon. But if we're asked to find a basis of this product space, what would you have to do? Well, consider this list of length 5, right? So in the first one, we have, so notice how 1, 2, and 3, these 3 vectors form a basis for this space, right? The polynomials of mostly degree 2. And R2, well, this vector here and this vector form a basis for R2. So what are we doing there? What we're doing is we're finding a basis for this space because any linear combination of all these 5 vectors, any vector in this product space, we can, I guess, create with a linear combination of these 5 vectors. And those five vectors are linearly independent and they span the space. Therefore, they're a basis of the product space. Right? So I do have a theorem here. Before I do move on to the theorem, though, I do want to answer this question. Are they equal? Well, short answer, no, they're not equal. And the reason being is because we get uh, V1 and V2 and R2 and R3, right? That's a list of length 2. R5 has a list of, actually I shouldn't even put V. I just will, sorry. Okay, V3, V4, and V5. So one is of length 2 and one is of length 5. So they're not really equal. They are isomorphic though, and it's exactly how you would think they are. So for example, in R2, I'm just going to draw down here. Ignore this theorem for now. In R2, we have V1, V2, and in R3, I'm just going to call these V3, V4, V5. So this is in R2 cross R3. And then in R5, we have V1, V2, V3, V4, V5. And well, as you can probably imagine, it's, like I said, they're not equal, but they are isomorphic. As you can obviously see, V1 to V5, injective, surjective to the vectors in R5. And some mathematicians might even say, oh yeah, they're equal, you know, they're isomorphic, they're equal. And I mean, it's not technically right, but it's pretty much the same thing. So that's the answer to that question in red. But now we can take a look at this theorem. Well, the theorem says, suppose V1 to Vm are finite dimensional vector spaces, then their product is finite dimensional, and the dimension of the product is equal to the dimension of the sum of each vector space. And this one, if it doesn't make too much sense or intuitive sense now, just think of this example. That's why I presented this example. This example kind of makes us see how this is going to work, right? So, for example, the first vector space we had here, the polynomials of degree at most 2, have dimension 3, right? This one has dimension 2. We added them together, gave us dimension 5, so the product has dimension 5. That's how this is going to work. We're going to take a basis of each vector space and then add it to our, put them in one list so that we can get a basis, which tells us that, I mean, the dimension will follow. So proof goes like this. We're going to choose a basis for each vj, again, like we did in our example. Then for each vector of each vj, we consider the element of the product of the vector spaces that equals the basis vector in the jth slot and the 0 in the other slots. So again, this is going off to the example. Consider an element in the product space. So this is 1. And the basis vector is 1. And then put a 0 everywhere else. Same thing over here. We had a 1 for R2. And then a 0 everywhere else. That's how we're constructing this basis. Therefore, the list of all such vectors is linearly independent and spans the product. Right? So it is a basis of the product. And the length of the basis is a dimension of V1 plus the sum of the dimension of the vector spaces. So again, this proof really just follows the example, what we did in the example. Make sure you have that down. and understand what's going on. So next we're going to be looking at products and direct sums. So sums, that's the symbol for them, so I put them there. If you don't remember direct sums, we looked at that, I believe it was chapter 1, I can't even remember now, or chapter 2. Early on in the lectures. So, suppose U1 to UM are subspaces of V. We're going to define a linear map that maps the product of those vector spaces to their sum, like this. It's explicitly showing us how. Then U1, the sum of the vector spaces, is a direct sum if and only if the mapping is injective. Right, so before we even continue with the proof, how do we show that a linear map is injective? Well, if you remember that, it's injective if and only if the only way to write 0 as a sum is where all the components are equal to 0. Right? So then it's injective if and only if the sum of the vector spaces is a direct sum, right? Because that's a condition from the direct sum, if we recall. And therefore, our theorem holds, right? Our mapping is injective if and only if the sum of the vector spaces is a direct sum. All right, yes. And again, this is fairly obvious if you're comfortable with direct sums. If not, you might want to review those. But this really shouldn't be too hard to follow. Unless, like I said, you might need a review. So we can move on to the second theorem that says suppose V is finite dimensional and U1 to UM are subspaces of V. Then their sum is a direct sum if and only if the dimension of the sum is equal to the dimension of the product. And again, if you're comfortable with direct sums, this should be pretty intuitive. Let's go ahead and prove it though. The mapping from the previous theorem is surjective, right? This is the previous theorem. This is surjective. So what can we say about that? Well, by the fundamental theorem of linear maps, the mapping is injective if and only if this dimension holds. Or sorry, this equality holds. Now, why is that? Well, to help you see this, let's call this, if you look up here at the theorem, this here is our space V, right? And what's the range of our mapping? Well, U1 plus dot 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 UM. Well, if they're injective, we should have, the fundamental theorem of linear maps tells us that the dimension of V should equal the dimension of the range plus dimension of the null space. Dimension, oh, I wrote that backwards. Dimension of null of the mapping, right? So V, we know, is up here. It's this, our product. The range is this here, as you can see from the theorem above. So it's injective. What does injective mean? That means that the null, the only thing that maps to 0 is 0, right? So it's 0-dimensional. So this we can pretty much, the dimension of the null space is 0. So therefore, that's why these two are equal, or as it shows up here, these two are equal. All right, so that's why that's saying this map is injective if and only if the dimension of the range is equal to the dimension of the vector space. Again, because the dimension of the null space will then have be 0. So if that's the case, then we can combine the theorems and show that the sum of u1 to um is a direct sum if and only if the dimension of the, oh, whoa, there's a mistake. Okay, so let me, why is this, that's what's wrong. Okay, this should go here. Sorry about that. That might be, when I said it was intuitive, I was looking at the notes in the book, and looking at it here, I hadn't noticed that we had that mistake. So yes, replace here, replace this. Let me just check if there are any previous theorem. All right, everything else should make sense. And just to add, here, for taking all the sums, if the only thing in our intersection is a 0 vector, well, then we should get that this equality, right? By direct sums. Remember, from a direct sum, the intersection of the subspaces can only be the 0 vector, but their union is a whole space. That's how you can intuitively see that that equality holds. Okay, so actually I should just leave that there like that. This is not true. Okay. So, I hope this was clear, direct sums. So we can move on to quotients of vector spaces. Now, quotients of vector spaces, you might have seen something really similar to them in abstract algebra. You might relate them to something called cosets. But we're going to be looking at quotients. So, the definition, here we're defining what v plus u is. So suppose v is a vector in V and u is a subspace of V. Then v plus u is a subset of V defined by v plus u for all vectors in U. So what the heck does that mean? Well, let's go over an example. Suppose U is in R2, right? It's a subspace of R2, and we define it by putting x to x. Then U is a line in R2 through the origin with slope 2, right? So let me bring up a picture for this before we even read on. This here is x to x, right? So we're at the point 10, 20 because x is equal to 10. But if x is equal to 0, well, then we have this point, our origin, and everything in between, right? Now, v here will be 17, oh, sorry, not plus 20, 1720. So 1720 here is in, or actually I should say v plus, oh, here it is. 1720 20 plus u is a line in R2 that contains a point 1720 and has slope 2. Now here, a common mistake I've seen students make is they think this point shifted here and think this point shifted here. Not really. And let me just be a bit clear about that. Let me erase this. So they are parallel. We know what parallel lines are, even though we haven't really defined them here from high school, middle school. We know what parallel lines are, which we will define. But for this example, this is our 0, 0, right? But if we add the 1720, right, the v, we get 1720. So this point actually shifted up here. And again, the point shifted up, but I mean, they remain they remain parallel. So in this point here, I know it's 7, 0. The reason I know that is because to get to, okay, so if I get u, I need a vector u, or x, 2x plus 1720 to equal 7, 0. Well, then I know that I'm subtracting x equals negative 10. So if x equals negative 10, then we have negative 10, negative 20, plus 1720 gives us 7, 0, and that's how we get this point here. You can work backwards. I don't want to say too much because I already feel like I'm confusing you more than anything. But just make sure you see how we're getting this new line by just adding that vector v, 1720, to the subspace u. So then we can define an affine subset, or affine. I've heard different pronunciations. Of v is a subset of v of the form v plus u for v in v and some subspace u of v. And here's where we define parallel. All affine subsets are said to be parallel of to u. Right, so we could have added another vector and maybe gotten this parallel line and then this parallel line, although my lines aren't that straight. But all the lines, there's infinitely many, we get that they're all affine subsets and they're all parallel to u. So again, an affine subset is said to be parallel to u. So suppose u is a subspace of v, then the quotient space is kind of like a quotient, right? V slash u is a set of all affine subsets of v parallel to u. So in this case, with this example, the quotient space v over u, or v slash u, are all the parallel lines to that line x to x, or that line right, x to x, or 1020, the original line. All those lines make the quotient space. So that's what quotient spaces are. So again, the set of all lines that have slope 2 make up the quotient space. In U, if U is a line of R3, right, so the Euclidean space R3 containing the origin, then R3 over U, that quotient space, is a set of all lines in R3 parallel to U. Right, and in R3, parallel lines follow the same rules. And luckily we can imagine what R3 looks like, right? Just three-dimensional, and that'll make up the whole quotient space. So those are two examples of quotient spaces. So now on to a pretty important theorem, one we're going to be referencing a lot. We're going to keep coming back to. Suppose U is a subspace of V and VW are in V. Then the following are equivalent. If V minus W is in U, then that's the same thing as saying V plus U is equal to W plus U. V plus U is equal to W plus U. And that's the same thing as saying V plus U intersect with W plus U is non-empty. So those two things are equivalent, right? They're the same thing. Not intuitively, we can't see this clearly. Maybe if you can, that's great. I definitely couldn't, so we will need a proof. So first off, we're going to suppose A holds and show that we get B. So suppose V minus W is in U. Well, if U is in U, then V plus U is just the same thing as, okay, so here, all we're doing is adding 0. So W and negative W. We're adding a W, subtracting a W, just to get this equality. But this now shows what? Well, if this is in U, and we add U, we get U. And then plus W over here. So we get that V plus U is in W plus U. Therefore, V plus U, well, like I said, is in W plus U. And we can do the same thing to show that W plus U is in V plus U. Therefore, showing that those two are equal. Therefore, A implies B. Now, to show B implies C, that's really not hard. If these are identical, they're not empty, right? Because U is a subspace. Then B obviously implies C, right? They're identical. How can their intersection be empty? So obviously B implies C. But now, suppose C holds, and we're going to show that A holds. So suppose C holds, that their intersection of V plus U and W plus U is non-empty. Well, then there exists a U1 and U2 in U such that V plus U1 is equal to W plus U2. And therefore, just like doing simple algebra, V minus W is equal to U2 minus U1. And again, U is a subspace. We have that addition is closed. So therefore, V minus W is in U. Right, so again, over here, because U is a subspace and it's closed under addition, we can, use these little tricks just like we did here. Use a subspace so we know it's closed under addition. We get that C implies A, and therefore all of them imply each other, so they're all equivalent. And again, we're going to be coming back to this one, this theorem. We'll use it for later theorems. But before we do, we should define what addition and scalar multiplication are in quotient spaces. They're simply like this. If you have V plus U plus W plus U, you add the V plus W, and then later the plus subspace, the plus u. Same thing with scalar multiplication, you apply that to the vector v, not to the subspace. Now, quotient spaces are a bit more complicated, right? They seem a bit, I don't know if weird is the right word, but definitely not like the ones we've dealt before, not like the vector spaces we've dealt before. So the question arises, is it even a vector space? Well, this theorem states that it is. Right? And we will go over this proof, but not entirely. This proof will mostly consist of proving that addition and scalar multiplication make sense, right? Because if those make sense, then you already have what addition and multiplication are, and it's much easier to show that it's a vector space. But we need to show that these operations do make sense. So suppose first that v and w are in V, and that v hat and w hat are also in V, such that v plus u is equal to v hat plus u, and w plus u is equal to w hat plus u. Right, so we're going to show that addition is well defined. So to show that it makes sense or that it's well defined, we must show that this equality holds. Right, they can't be two different sums. So by our previous theorem, we have that v minus v hat is in u. Right, we're using part A of the previous theorem, and w minus w hat is in u. Again, so we're using these two parts, right? Well, because u is a subspace of v and it's closed under addition, we have that v minus v hat plus w minus w hat is in u. And therefore, well, it's just saying the same thing, that v plus w minus v hat plus w hat is in u. And what does that state? Well, that this equation does hold. So to be add a bit more detail, we can just call this v as this v here, and we call this w over here, right? So that's in u. So then our b follows, right? V plus u should equal w plus u, and v is v plus w, and then plus u, which is equal, and then our w is v hat plus w hat plus u. So that's why we get this equation. Right, so we really are just using our previous theorem. Make sure you can follow that. If you need a pause, go back. But that's what we're using. So then we're showing that indeed addition is well defined and it makes sense, right? So addition on the quotient space v slash u makes sense. Similarly for lambda, because u is a subspace of v and it's closed under scalar multiplication, we have that lambda times v minus v hat is in u, right? Because, well, this is in u, and because it's closed under multiplication, we know that multiplying by lambda is in u. Therefore, lambda times v minus lambda times v hat is in u. Therefore, okay, again, it says our previous theorem implies that this equation holds, Again, here, A, this is B, we're using A implies B. So just make sure you can follow that. We're just using that property of the previous theorem that A implies B, so we can get this equality, therefore showing that its multiplication is well defined, so it makes sense on the quotient space. So now that you have addition and multiplication, you can prove that it's a vector space. I'll leave that up to you because as you can see, it's going to take up a bunch of space and it's a, well, a chapter 1 exercise. Always a good exercise though, because we are dealing with nothing but vector spaces. So our last slide that we're going to go over goes over, I included this picture here. It's similar to cosets, right? From abstract algebra, we have that partition. That's what we're kind of dealing with, right? But now in, well, linear algebra and vector spaces and showing properties of them. We're going to be going over a quotient map. So here, suppose you have a subspace of V, then the quotient map pi is a linear map that maps V to the quotient space V over U. And how do we define that map? We take the vector V and we map it to V plus U, where again, U is a subspace of V. So again, here pi is a mapping. It is not the irrational number you're thinking of, 3.14, so on and so forth. So again, that's how we're defining what a quotient map is. You could, and actually, I suppose a good exercise would be verifying that this is indeed a linear map. But we'll be presenting the theorem that if we suppose V is a finite dimensional vector space and U is a subspace of V, then the dimension of V over U, of that quotient space, is equal to the dimension of V minus U. Does this make sense? Again, this is a theorem you probably go over in your abstract algebra course, but we're looking at vector spaces now. Really similar. And to prove this, as you can probably imagine, we're going to be using the fundamental theorem of linear maps, which is why this proof is so short. So let pi be the quotient map from V to V over U. Well, from the previous theorem, we see that the null space of the quotient map is equal to U. And this shouldn't be really hard to see, just what maps to U. Well, if you put V as the zero vector, we get U, right? That the null space of the mapping is U. And again, where this is, so when I say from a previous theorem, again, referring back to not showing that the quotient space is a vector space, but the one before that where we had A implies B implies C. Right, using that we can show that the null space of the mapping is U. So now we can use our fundamental theorem of linear maps. Right, so clearly the range is the quotient space as how the mapping is defined. So the fundamental theorem of linear map tells us that dimension of V is equal to dimension of U plus the dimension of the quotient space, and we are done. So if null space of the quotient map is U, then what can we say? Well, each linear map T on V induces a linear map T tilde or T with a squiggly, as some students say, on the quotient space V over null space of T. So suppose T is a linear map from V to W. We're going to define this new linear map with the domain V over null of T, that quotient space, to W by taking V plus null of T, the null space of T, to T of V. And again, does this definition even make sense? Well, it does. And actually, I may have shown, no, I did not show. So before we do go over that theorem, I'll just show you the property. So for example, if we had U and V in the vector space V, and we had U plus null of T equal to V plus null of T. So again, here, this null T is taking the spot of U, right? Instead of having U, we're having the null space of T. So by, again, the previous theorem we had seen, this implies that V minus, or U minus V, is in U, or not U. In this case, we're using null T, so is in null T. So therefore, T of U minus V is equal to 0, which implies that T of U is equal to T of V. So that's how we can show that this mapping does make sense. So we can go on to the theorem. And before we even do prove it, just make sure you understand this definition. Don't be too intimidated by it. Null space of T might throw you off, but it really should be as intuitive as you might think. Right, so in this case, the only thing we're adding is the null space of T. If it helps you, don't look at that. We have that TV is equal to TV. But we're adding the null space, which if you're comfortable with the null space, you understand it. You know it. I shouldn't say doesn't do much, but it really doesn't make things complicated. And in fact, these theorems are, or these properties of the theorem are quite easy to prove because of the fact that this definition isn't as complicated as it might seem. So the first one, first A, I'm skipping this one because, again, proving something is a linear map, chapter 2 maybe? Chapter, that's a good exercise. But I'm going to go with T, our new mapping, T tilde is injective. So suppose V is in V, and this mapping is equal to 0. What does that mean? Well, because of how this is defined, we get that TV is equal to 0, right? We're just getting that from the definition. Therefore, V is in the null space of T. And by previous theorem, we get that V plus the null space of T is equal to 0 plus the null space of T. So again, we're using A implies B, from our the previous theorem from the last slide, right? Like I said, we will be using that theorem a lot. And therefore implies that the null space of T tilde is equal to 0, therefore T tilde is injective, right? That's the condition we need for injectivity. Again, by just how T tilde is defined, it's pretty straightforward to see that by definition the T tilde we see that the range of t tilde is indeed the range of t. And finally, part B and C. Again, we can use the that theorem that just basically says the condition for an isomorphism, or it's isomorphic if and only if it is injective and injective and surjective, which B and C tell us. So we can get that T tilde is an isomorphism from the quotient space V over null space of T onto the range of T. Again, because it is bijective and therefore isomorphic. This might have been the most difficult slide to grasp at first, but make sure you kind of go over details, and you'll pretty much see that this isn't really a complicated slide. So that'll conclude the next lecture or section. Duality is probably, besides it being the longest, it is a lot of information. So we'll be looking at that next.